Morning, everyone. So yesterday we started looking at acid-base buffers. I'm going to start you off with a warm-up question just to make sure we're clear what is a buffer solution and how it works. We're going to build on what we learned last day. We learned one method of making buffers yesterday. Today we'll rehash that method, and I'll show you one other method, and we'll see a little bit of the math come into play. So just for a quick warm-up here. First question, I just want you to define buffer. What is a buffer? Right. And question number 2, based on your definition and based on sort of the job of a buffer, which of the following mixtures here, so which mixtures below can form buffer solutions? Okay, so let's do a couple mixtures, not multiple choice, you just choose all these options, any of the options that are correct. HCl and NaCl. Let's do our Chiku and an acetate salts. Let's do lithium there. Let's do NH3 and NH4I and one more CH3 NH2. Okay, so I'd encourage you just to pause the video. You can try it out for yourself. Okay. Assuming you've done that here, let's define a buffer. Okay. A buffer is a solution containing, they like this language of appreciable amounts. It just means I have good amounts of both. Right. What does appreciable amounts look like? It could be like 0.1 molar, it could be 1 molar, right? I have good chunks of both. It's not just negligible amounts. So it's a solution containing appreciable amounts of either the combinations are going to be weak acid, and we've artificially beefed up our conjugate base, or we can have a weak base, and we're going to beef up our conjugate acid. Those are the two ways I can end up making a buffer system. What's the job of a buffer? Containing appreciable amounts that minimizes, doesn't stop the pH change, it minimizes large pH changes or pH jumps upon, it's important here to say small additions. We had talked about a buffer capacity last day. Basically, there's a limit to how effective your buffers are. Only small additions of acid and base. Okay, so a couple key notes. When we use this term here, buffer, this sort of leeway, this sort of cushion on either side, a buffer has to be able to buffer both acid and base, right? All buffers do. Towards the end of last class, we talked about what's an acidic buffer or basic buffer. The acidic part doesn't tell you, oh, I can only buffer acid, or basic buffer only buffer base. The acidic and basic actually refer to the pH at which they actually buffer. And it turns out, if I have a combination, a weak acid conjugate base here, usually the pKa is actually less than 7. So therefore, where it actually tries to control the pH is actually in the acidic region. So that usually refers to an acidic buffer. I buffer in the region that's lower than 7, whereas if I have a weak base and a conjugate acid, usually the pKb is lower than 7, so it's going to be basic. Again, all buffers need to buffer both additions of acids and bases, but in this case here, the basic actually refers to at what pH does the pH get controlled. And in this case here, your pKb is going to be something less than 7. pKb is sort of like on that pOH scale, so less than 7 actually means basic. Do note here, don't say the pH stays constant, even though we're going to do that as a simplification in our math later on, but it just tries to minimize it. It tries to hold the pH constant as long as possible. I just keep this sort of idea in mind here. If I plot the pH versus, let's say, volume of base that I'm adding, we're going to have a situation where at the buffer, we're going to be at some special pH. This is going to be, say, the pKa of your chemical. Because the buffer is able to moderate additions of acids, it doesn't let the acid drop the pH so quickly. It's actually going to level off. It takes a little while until the chemical runs out. So the pH does change, but it doesn't change by much. You can also buffer base. By adding base here, it's going to climb by a little bit here before shooting up some more. Right? So the buffer is basically trying to hold the pH on both sides. If it does it in the acidic region, it's an acidic buffer. So the keynote here is how does it do it is because of an equilibrium system. That's why we needed something that was weak. So when you're answering question number 2 here, if you're noticing something that's going to be strong, that's not going to be in equilibrium. So for example, HCl, we know it's a strong acid. HCl one-way arrows forms H plus and Cl minus. In fact, it's not even in equilibrium, but by the time this reaction is done, I actually have no reactant left over. All of it's H plus and all of it's Cl minus. I don't have the ability to shift left or shift right. So because that's strong, this one here cannot be a buffer. Okay. How about this other one here? I have acetic acid, good. This one here is a weak acid. So I can say my Chiku. This one here is going to be in equilibrium, so it looks promising here. If it's just a weak acid by itself, again, the Ka constant is actually very low. I don't get enough H+, I don't get enough acetate. I may be able to shift right upon additions of base, but if you add acid, I'm going to run out of acetate very quickly. Now this salt here looks a little bit weird, right? Usually you have the metal in front, but basically this is a lithium salt that contains acetate. This one here artificially beefs up the amount of acetate for you here. Again, the amounts don't have to be exactly equal to each other. Sure, we had a really nice situation if they were equal, the pH is equal to the pKa, but they just have to be appreciable. If this one were like 0.9 molar and this was 1.1 molar, still a buffer. It still works, no problem. So this one here can be a buffer. Ammonia and the ammonium salt here. Ammonia is a weak base, good. It has an equilibrium system. I'm going to write the complex equation. So NH4 plus and OH minus. In this case here, again, as a weak base, the constant is very tiny, heavily reactant favored here. I'm not going to produce a lot of ammonia, a lot of hydroxide. In this case, so far, what can I buffer? So far, I have a good amount of NH3. I can shift to the right. What would cause this to shift right? If you added H plus at this point here, that pulls down the hydroxide. I can shift right. I can buffer small additions of acid right now. But for a buffer system, you need to be able to buffer both acids and bases. What I need to do is I need to artificially come in and beef up my amount of ammonium, and that's what the salt does. Well, where did the iodide come from? You're not going to have a bottle of just pure NH4 plus. This guy here, as an ammonium salt, it completely breaks to form ammonium and iodide. Iodide is just a spectator. I just care that it has actually beefed up the NH4 plus. And yes, as you're adding the salt, it would have already shifted over, but it's not that hard to get a situation. Now we set our buffer, now we have good amounts of both ammonia and NH4 plus. How about this methylamine here? Methylamine here is a weak base. I just wanted to throw that in there. But in this case, for methylamine, as a weak base, if you're not coming in and beefing up the amount of salt somehow, we can't actually be a buffer. So in this case here, just the weak base here, I don't have enough NH4, CH3, NH3 plus, or hydroxide. I cannot shift in the other direction. For the time being, it's not a buffer. Although what we're going to do in this lesson here is we're going to find another way of making a buffer, and even without adding the conjugate salt here, there is a way for me to get appreciable amounts of both conjugates so that I can shift left or shift right. Okay, so this is on the back side of your notes here. Earlier, we had derived that a buffer's pH is equal to the pK of the weak acid when it's composed of equal amounts of acid and base. Let me just derive that for you again. The Ka, let me just do a generic equation. As a weak acid, it runs into water, it donates a proton, it becomes A minus and hydronium. So therefore, Ka is going to be A minus times H3O plus divided by HA. Water is a liquid, so we can ignore it. This Ka expression is always true. Now, there was one special point, assuming that your conjugate acid amount and the conjugate base amount, HA and A minus, were equal. That's an assumption. That only happens at one point during your curve. These two terms are canceled out. Therefore, we can say Ka equals H3O plus, or negative log both sides. The pKa is equal to pH. So if I just am given some random chemical and I want to know, okay, I know it's weak, but I want to know what pH it buffers at, you look at its Ka. If you take pKa, that pKa coincides with, this is the pH at which the buffer is working at maximum capacity. The concentrations just have to be equal to each other. We saw a situation last day. It could have been 1 molar, that was the same. Even after diluting the buffer had no impact. You dilute it by factor 1 into 10, 0.1 and 0.1, the HA and the A minus still cancel out. The pKa is still roughly the same as the pH. Okay. Obviously, sometimes the concentrations are not going to be equal, especially, so let's say we have a situation, we have 1 molar HA and I have 1 molar A minus. Let's say I have added a little bit of acid. So I add a little bit of acid, good, I have appreciable amounts, I can shift to the left. let's have a situation where my A minus has dropped by a little bit. Maybe it's 0.9 molar, maybe it's now 1.1 molar. Okay? So at this point here, this simplifying assumption doesn't work anymore. If only we had another way of finding pH. Now up to this point, we've been mainly looking at pH. pH is supposed to be, by definition, pH is supposed to be the negative log of H+. First thing is the H+ would have been really tiny at the beginning. The weak acid here is not really good at ionizing. You're going to have a really small amount of H+ to begin with. You suddenly toss in a bunch of H+. This value here goes way up, and it's going to start coming downwards. I'm not necessarily sure how much it comes down to, but I know it's not going to be back down to before your addition. So what we're actually going to do here is we're going to try to find another way. Can I actually find the pH without looking at the H+? And this sort of derivation from yesterday sort of hints at, maybe. If I can somehow rearrange this Ka expression here, this Ka expression can tell me some connection to H+, and then I can take the negative log of my expression to actually get pH. So, in a situation where they're not equal, right, it's still a buffer system, I still have good amounts of both, I still have some ability to shift left or shift right, we can still calculate the pH of a buffer solution. This one here will involve my Ka expression. Right. So I'm just going to copy it down here, H3O plus A minus divided by HA. So that was just a generic acid equation. I'm focusing mainly on this H plus term because I need the negative log of H plus to get pH. Everything that's not H plus, I'm going to kick over to the left side. So let's try that out here. The Ka, I'm going to multiply the HA up, and I'm going to divide the A minus going down. That actually mathematically gives me my H3O plus. So long story short here, what this actually allows me to do is it says, even if you're having a hard time telling me how much H plus there is exactly, if you know the amounts of conjugate acid and conjugate base present, I can play around with this math here. I can calculate the H plus, and then you can do the negative log, then you can find the pH. Since we are going to do the negative log, what I'm going to do now is I'm going to take negative logs of both sides. So negative log of Ka, this expression is going to look a little scary for now, over A minus is equal to negative log of H plus. Perfect. The right-hand side already looks really neat. This side here is going to end up just as pH. Let me just clean this up a little bit here. Remember, we have a few log rules. Whenever you have log of A times B, that's log of the first thing plus log of the second thing. And in a similar fashion, if I have log of, let's do C over D, that's going to be log of C minus log of D. The reason why I re-emphasize it here is I have a negative log of two things being multiplied and these things here being divided. Okay. So what I'm going to do here, first thing I'm going to break up is Ka times the HA A minus product. So let me just rearrange that. So negative log, I'm going to pull the first term first. So Ka, I'm going to add, it's going to be a negative log. I'm going to leave this term here as HA over A minus. I'm not going to do the subtraction just yet. This is going to equal to negative log of H plus. Hopefully you can match that up here. And now what I'm going to do is I'm going to just simplify some of these terms here. Well, hey, this is negative log of something, so this one here can be called pKa. This is negative log of H plus, well that there is pH. If you want to find the pH, earlier it was just equal to pKa, but this time because the concentrations aren't equal, there's a slight correction term here. I don't really like the fact that there's a minus here, so what I'm going to do is I'm going to bring that minus back up into the power, and I'm just going to flip the fraction. So this is actually going to be plus log of A minus divided by HA. Okay. It is still related to the product concentrations here. This equation is given a name. This is called the Henderson-Hasselbalch equation. This one here is actually given on your formula sheet, but it's easy enough just to derive it from the formula. Let's verify if my simplification was still true. What if A minus was equal to HA? Well, these two things would divide out, so they give you 1. Log of 1 just gives you 0. Yes, pK equals pH. So this one here is just a little bit more generic than what we had from before. It gives us some way of actually measuring that correction term. Okay. So before we go through a practice question here, I want to just hint at there is actually two ways of making a buffer system. A buffer system just has to have good amounts of both the HA and the A minus, and we've just found an equation. If you know the ratio between the conjugate amounts at that particular point, I can actually figure out the pH at any point during the curve. There's two ways of doing this. The easy way is the one that we did from yesterday. let's directly mix something that's weak and let's toss in the conjugate. So for example, let's take our acetic acid again. This is an equilibrium, and I've drawn this multiple times here just so it reinforces that idea for you here. Acetic acid by itself is not a buffer. Being weak, the Ka value is too tiny, it doesn't actually have a lot of acetate. What I want you to do is I want you to add a salt that contains this conjugate here to artificially beef up this amount. Once I have enough of both of these, then this equilibrium can shift left or shift right, no matter what it wants. The key about this salt here is you just want to make sure it's a soluble salt. So that's why like alkali salts are always soluble. So that's why typically we throw in, lithium acetate or sodium acetate. Those are guaranteed to be soluble. Again, the concentrations don't have to be exactly equal. Sure, the buffer would be sort of in the mid of its buffering capacity if it really was, let's say, 1 molar and 1 molar, but still a buffer as long as I still have amounts present that I can shift left or shift right. The complicated way that I'm going to start introducing to you in this lesson here, the complicated way is start only with a weak acid. This time, I'm not going to add in the salt, right? That was the easier way of doing it. Is there another way for me to produce acetate? What I'm actually going to do is I'm actually going to start neutralizing some of this acid. As this one here gets neutralized, the conjugate acid by itself will be forced into the conjugate base form. There will hit a point where these two amounts are appreciable. So what I'm doing here, as I'm creating the buffer system, I'm starting with the weak thing, weak acid. I'm going to add in a strong base to force some of it to neutralize. Or if I have a weak base, I'm going to add in a strong acid, usually HCl or NaOH, just to produce the conjugate. So this is how this part looks like here. I'm going to have, overall, my equation is going to be CH3COH. Because this one here is currently a weak acid, I want to neutralize some of this weak acid. So neutralizing it, I'm going to add in a strong base. This one here is going to be a one-way arrow because this one here is just a neutralization reaction. Basically, the hydroxide starts killing off some of the H+. So the equation itself, NaCH3COO, so that guarantees that I end up forming acetate, and I end up getting water, right, which is expected out of a neutralization reaction. If I just focus in on what about the weak acid equilibrium itself, well, this one here would have been CH3COH in equilibrium with H plus and CH3COO minus. Let me put a few numbers to this here. Let's say I start off with 10 molar acetic acid. Initially, before I added in any NaOH, it's just 10 molar. If this one here were 10 molar, I have a lot of the acetic acid. I don't have a lot of H+, I don't have a lot of acetate. It's still going to be like 0.1, 0.2 molar, right? The Ka constant is so tiny. I'm going to think at a couple instances in time here. So this one here, let's say is t equals 0. At equivalence, right, there's a name we haven't seen in a while. At equivalence, the moles of H+ has canceled out the moles of base. You've perfectly counted the acid particle and you perfectly dropped in the base to neutralize it. So what would I need to actually reach equivalence? If you have 10 moles or 10 molars worth of acetic acid, I would need to have added 10 molar NaOH. In that situation here, if I had 10 molar to begin with, I react 10 molar worth of the base, I'm now left with 0 molar acetic acid. The base has neutralized as well, so I have 0 molar of the NaOH. Equivalence point has basically killed off both your reactants, and now we're left with our salts. We've now produced 10 molar of our sodium acetate, and we produced, water is a pure liquid, so I don't worry about it. So that's what happens at equivalence point. I'm not actually going to wait to equivalence. I'm going to look at the point, what about half equivalence? I know I needed 10 moles, or 10 molars worth, to end up canceling everything out, but what if I've only added in 5 molar? Well, what would happen there is, by adding in 5 molar, right, there is base present. The base is going to slowly kill off the acid. Because the change line is, well, I shifted, I gained by 5, I'm going to react away all 5. My acetic acid is also going to drop by 5. I'm going to be left with 5. So, at the half equivalence point here, I would have lost 5 molar. 5 molar would have got converted over. I would have picked up plus 5 molar of your sodium acetate. What I'm saying here is I would still have 5 molar. I still have some conjugate acid present, but now I also have some of my base present. Sure, the 5 molar is not as high as the 10 molar was before, but you notice, because I started out fairly high of a molarity, I notice at this point, hey, I have good amounts of conjugate acid, I have good amounts of conjugate base. Whoa, where did the NaOH go? Well, the NaOH was actually used to convert the acetic acid into this acetate form. But when I start looking at the buffer system, I'm just focusing on the weak acid itself. I have a situation where I have good amounts of both. At this half equivalence point, we are at a situation where I can shift left or shift right, no problem. And I have not actually added in any salt containing the conjugate. So let me just plot this out on a curve for you here. We'll do this in more detail in the upcoming classes. I'm going to plot pH versus, in this case here, I'm adding moles of NaOH, right? So at first, we start off, we have 10 molar acetic acid. I know it's a weak acid, but 10 molar is actually fairly high. If we do 7 as a dividing line, probably my pH is on the order of maybe pH 2 right now, okay? So that's my initial point here. This is upon adding no NaOH. By the time I add the equivalent of, we said 10 molar NaOH, I have perfectly neutralized all of your acid. When I perfectly neutralized it here, in this case here, we're going to come back to this in a little more detail. We would have expected that the pH, well, if the acid is gone and the base is gone, shouldn't the pH be 7? We're going to come back in a later lesson. We're going to see that the equivalence point, it's actually a little bit higher than 7. And we'll talk about why later on. But there we go. No real surprise. We start off just having the weak acid. As you steadily add base, I would expect the pH to steadily climb. We're going to hit a point. This point here is called the half equivalence point. At half equivalence, we would have added 5 molar worth of NaOH. At that point here, when you've added 5 molar NaOH, the NaOH would have canceled out. We've pulled down the 10 molar. Now we only have 5 molar of the acid left. We've also produced 5 molar of the conjugate. We've now produced a situation where at the half equivalence point here, it's now naturally formed a buffer. Naturally, we have appreciable amounts of both acid and base. So the pH is going to stay relatively constant. So outside of this buffering range here, the pH is not going to drop down very quickly. It's not going to increase very quickly. So we had been able to produce this buffer system without artificially producing, just throwing in a soluble salt. Outside of the buffering capacity, when I eventually run out of the 5 molar, eventually we will hit a situation where I have no more weak acid again. Now any more addition of base will suddenly cause this one here to shoot up, and this one here to shoot down as I leave that case. So we've made a buffer solution. The buffer solution is supposed to maintain pH. It's supposed to be able to buffer both if I add OH minus or if I add H plus, which it does, and we've actually created it. We've formed the conjugate by neutralizing some of the weak acid. Way more complicated than just adding the conjugate, right? So those are the two main ways. Just to re-emphasize here, we are going to use this Henderson-Hasselbalch to actually deal with the numbers, but there were two ways of making the buffer system that has both conjugate acid and conjugate base. Okay. So let's try out this question here. We're going to consider a buffer solution that was prepared by mixing 1 mole of ammonia with 1 mole of ammonium chloride. They're back to the easier way, just adding a salt that contains the conjugate. Kept the numbers fairly easy, 1 mole in a 1 liter container, so the concentrations are 1 molar. Let's start off here. Ammonia here as a weak base. I'm going to go right to the complex equation here. Ammonia is going to steal a proton from water. This is going to end up becoming the ammonium ion, leaving behind hydroxide. I have my buffer system set up. The ammonia concentration is currently 1.0 molar. The ammonium chloride, this one here is a salt. This one here breaks up to form NH4 plus and Cl minus in a 1-to-1 ratio. I don't really care about the chloride, it's just going to be a spectator, but at least the NH4 plus is now going to be 1 molar. It's diluted to 1 liter, so that's why the concentration is 1 molar. I want to find, well, what is the pH of this buffer? Now, normally for pH, we would zoom in and we'd say, okay, let's try to find hydroxide, let's do our Ka calculation, whatever. Remember, for a buffer, the Henderson-Hasselbalch equation actually gives you a link between pH based on the Ka from the table and also the starting amounts. So if I just rewrote that formula here, my Henderson-Hasselbalch equation says the pH of my buffer system is basically my pKa of the chemical plus the log of the A minus divided by the HA concentration. And again, we've kept the numbers fairly simple here. Not only are both of the numbers 1 themselves, I just care about this ratio here. If I go 1 divided by 1, these two numbers here end up canceling out, and a log of 1 is just going to be 0. Basically, then my pH is going to be the pK at this particular point. The pKa of this chemical is given to me here. Actually, on the table, table 21, they actually give me pKb of the ammonia here, because this one here is a base. pKb is actually 4.75. how do I go from pKb to pKa? Now, I'm not suddenly saying, oh, what if ammonia was an acid? Remember, the link between Kb and Ka were for conjugates. What is the pKa of the conjugate acid? In this case here, we're going to just go 14 minus this 4.75. You can look back in earlier lessons for that derivation there. By doing this subtraction here, 14 minus 4.75 gives you your corresponding pKa is actually 9.25. So let's just verify here. Well, we are a basic solution. Sure, we've shifted a little bit by adding the conjugate, but overall this is a base, so I would expect that the pH right now that we're buffering at is actually in the basic region. Perfect, 9.25. Now what I'm going to do is I'm going to do a little bit of a strange sort of ice table kind of question. Because this is a buffering system, now I'm going to add 0.1 moles HCl into my 1 liter container, so I'm actually going to add 0.1 molar. So I'm going to take the same equation here. I have NH3 in the presence of water. This becomes NH4 plus and OH minus. I'm going to do my ice table here. My ice table will be slightly extended here. In this case here, I had a buffer, 1 molar of my conjugate base, 1 molar of my partner conjugate acid. What I've decided to do is I decided to poke at the equilibrium. I'm going to call this a stress line. This is sort of similar to what I did earlier. I'm going to stress it out by adding 0.1 molar H+. Right? Now, H+ is not in the equation, right? How could it be in this expression? Well, we know the H+ and the OH- always react in a 1-to-1 ratio. They're going to kill each other off. Now, for starters, as a weak base, it didn't ionize very well, right? It didn't manage to give a big amount anyways. Usually, they just say small, okay? But suddenly what you do is you suddenly come in, you add 0.1 molar H+. The H+ is going to kill off the OH-. It's going to suddenly pull this concentration downwards. As it pulls this concentration downwards, because I'm weak, because I'm in equilibrium, I can then shift to the right. What's going to happen is I'm going to try to get rid of this change. We're going to do a simplifying assumption here. Usually Le Chatelier just counteracts your change. It doesn't really bring it down to what it was normally. But just for simplification, let's pretend 0.1 molar H+ is completely gone. Let's completely neutralize it. Well, how much NH3 would it take up? Because this is shifting to the right, this one here would drop by 0.1 molar. This one here would go up by 0.1 molar. Right? One side is plus, one side is minus. Okay? So we're going to do the math here. We have 1 minus 0.1, so that gives me 0.9 left over. 1 plus 0.1, now I have 1.1. Now they're not equal to each other, but still a buffer because I have appreciable amounts, good amounts of ammonium and ammonia that can still end up shifting left or shifting right. Now just let me clarify this a little bit here. On the ice table, we are tracking the hydroxide concentration. So in some sense, I shouldn't really be adding the 0.1 molar H+ like this. I just know that if I'm going to add 0.1 molar H+, that's going to use up 0.1 molar of the hydroxide. So what's going to happen at first, this part here is like I'm going to lose 0.1 molar hydroxide. And as I shift to the right, I'm going to end up gaining 0.1 molar, this part here. Even if you track in H+, it's going to be minus. This part essentially means I'm going to try to regain. In a perfect world, if I get back to 0.1 molar H+, that's what it should be. And basically what I'm going to end up with here is, again, a problem. It's just going to be small. It may not be identical to what it was initially. Fortunately for us, the Henderson-Hasselbalch equation allows us to actually calculate the pH without worrying about the OH- or the H+ like we've done in previous. For a buffer solution, we can go straight to our Henderson-Hasselbalch equation. What is the pH? Well, it's given by pKa plus the logarithm of A- divided by HA. If you know the ratio of the conjugate amounts left over, this will actually tell you the new pH. So let's just punch in here. Earlier we had said the pH equal to pKa. This is the pH right now was 9.25. That 9.25 was the same. But now my conjugate acid and conjugate base form, my conjugate acid form is 1.1 molar. So 1.1 is on the bottom. We have 0.9 up top. That's a small correction term here. 9.25 plus the log, make sure you use brackets, 0.9 divided by 1.1 gives us here the pH has changed, even assuming, right? So here we made an assumption. Assume the shift cancels the stress completely, even upon that sort of slightly simplified model here. We still see that the pH does change. Do a mental check for yourself. I have added acid. I expect the pH to drop. In this case here, instead of dropping, like 0.1 molar could have been a change of almost 1 pH unit, the pH here has only dropped by 0.09. Okay, so the decrease here has been really, really minor. So pH has changed, but not by much. Okay, because I still had the ability to shift over. You can add an even more 0.1 molar, you can still bring it down, it's still going to drop, but as long as I still have NH3, as long as I can still shift over, I can still moderate how quickly that pH changes. Okay, so get a little bit of practice using these Henderson-Hasselbalch equation. You don't need to memorize it. It's easy enough to just derive from the Ka expression. If not, it's also on your data booklet. Okay, pick it up from there. Thanks, guys.